Electron displacement effects in covalent bond. So these are actually necessary to predict the products of a reaction. So this displacement of electrons in a covalent bond can take place either by the influence of a single atom or a group of atoms present in the molecule. And this can also takes place in the influence or under the influence of an attacking reagent. So, as a result of this, carbon chain gets polarized or destabilized. And result of this, we see four different types of effect. They are inductive effect, resonance effect, mesomeric effect, and hyperconjugation effect. Amongst this, inductive effect and resonant effects are examples of permanent effects, while the rest two, that is mesomeric effects and the hyperconjugation effects, are found to be temporary effect. Inductive effect. So the permanent polarity produced in carbon chain due to the partial displacement of a sigma bonded pair of electrons towards a more electronegative atom or a group, right? So in the example CH3 CH2 Cl, chlorine is more electronegative than carbon, and the shared pair of electrons between carbon and chlorine are pulled more towards chlorine. As a result, chlorine develops a partial negative charge and the carbon has partial positive charge, which in turn draws electron from the next carbon, thus giving the second carbon also a partial positive charge. So here the effect can be continued, or the presence of this effect is felt to a second carbon, and in rare cases it is the third carbon, which rarely shows a positive charge in nature. And the effect can be studied as two types: atoms or groups of atoms that pull the electrons more towards itself, or to the released towards carbon. First one is the negative inductive effect. So an atom or a group of an atom that is attached to carbon atom chain is more electropositive than carbon chain acquires partial positive charge, and this is known as the negative inductive effect. The examples are nitrate group is greater compared to cyanide, is greater compared to carboxylic acid, is greater than fluoride, is greater than chlorine, is greater than bromine, is greater than iodine, or greater than any alkoxy radical, which is also greater than the phenyl group. And these are also called as the electron withdrawing group. So when these groups are attached to the carbon chain, they will definitely pull the shared pair of electron towards themselves, giving carbon a partial positive charge. Thus, they are called as electron withdrawing group. The second type is the positive inductive effect. So, an atom or a group of atom attached to the carbon is less electronegative than carbon, then the carbon chain acquires partial negative charge. Such an effect is known as positive inductive effect. And the examples are a tertiary carbon atom, which is more than a secondary carbon atom, which is greater than a primary carbon atom which is greater than a methyl group. And these groups are also called as electron donating or electron releasing groups. And what are the features of this inductive effect? What effect does this inductive effect produce or result in, and where do we find them? So this kind of effect operates in saturated, that is aliphatic hydrocarbons, and unsaturated system, that is aromatic hydrocarbons. And these partial charges are produced. The strength of the effect decreases with the increase in distance from the group that is attached to the carbon. And this effect is always found to be permanent. It is an irreversible effect. The second effect is the electromeric effect. So, electromeric effect is nothing but the polarity produced in an unsaturated compound, and that too in presence of an attacking reagent. So this involves a complete transfer of pi electrons to one of the bonded atoms. So this compounds generally should have a double bonded carbon carbon system. So this electromeric effect can take place only in unsaturated hydrocarbon. I mean to say, carbon should always be attached to another carbon through a double bond. So this double bond has one sigma bond and the other one is a loosely bound pi bond. And there are two types of this electromeric effect. The first one is positive electromeric effect. So if the migration of pi electrons and the attack of the reagent is towards the same atom, then the effect is found to be positive electromeric effect. So in the reaction, carbon carbon double bond, so when this is approached by an hydrogen positive ion or a proton, the pi electrons are moving to carbon, the first carbon. The pi electrons, I repeat, the pi electrons are moving to the first carbon. So when electrons are moving to the first carbon, then the carbon has a negative charge and the second carbon has a positive charge, and thus the attacking positively charged hydrogen ion will definitely attack the carbon which is negative in charge or which has electron rich region. So here the attacking reagent is H plus, which is otherwise called as an electrophile. So I repeat, in the carbon carbon double bond, if the pi electrons are moving towards the first carbon is negative in charge and the second carbon is positive in charge because it loses electrons, and definitely the approaching or the attacking reagent H plus, when it meets this carbon carbon double bond, it will attack the carbon which is electron rich, and hence we have carbon plus carbon hydrogen. So such an effect is known as positive electromeric effect, that is the migration of electrons, that is particularly the pi electrons and the attacking reagents is towards the first carbon, and therefore this effect is a positive electromeric effect. Next is the negative electromeric effect. Now here it is the reverse case of positive electromeric effect. If the migration of pi electrons and the attack of the reagent is towards different carbon atoms, then the effect is known as a negative electromeric effect. So in this example, we see the pi electrons are moving towards the second carbon, sorry, pi electrons are moving towards the first carbon atom, and so the first carbon atom is negative in charge. I mean to say it is rich in electrons, and now the attacking reagent, a nucleophile, which is also rich in electrons, does not attack the first carbon. However, it attacks the second carbon, which is positive in charge. Thus, here we see the migration of pi electrons and the attack of the reagent is towards different atoms. Hence, this effect is also known as a negative electromeric effect. And the results of this electromeric effect. So, electromeric effect is a temporary effect, and unit charges are involved here, or unit charges are produced, and this type of electromeric effect operates between two atoms that are bounded by pi electrons only. So bounded pi electrons are possible only in carbon carbon double bond and carbon carbon triple bond compounds. So, approach of an electrophile results in an positive electromeric effect, and the approach of the attacking reagent, that is nucleophile, always results in the negative electromeric effect. Thus, pi electrons always migrate towards the more electronegative atom. So, I repeat, pi electrons always migrate towards the more electronegative atom. So, the next concept is resonance. So, this resonance is also known as mesomeric effect. So, it is the phenomenon in which a compound is represented by two or more structures. So, it is the polarity produced in the molecule by the interaction of two pi bonds or a pi bond and a lone pair of electrons. And here there are two types, and these are generally represented as capital R or capital M. So, capital R or capital M effect, the positive resonance effect or the positive mesomeric effect. So, here we find the migration of pi electrons or a lone pair of electrons away from the group that is attached to the conjugated system. So, conjugated system means where we find a continuous single bond and double bond. A continuous single bond and double bond. Example in case of benzene. Right? So, the best example we have to study here is amino benzene. This is C6H5NH2, or an amine group NH2 group attached to benzene ring. Nitrogen has a lone pair of electron. So this lone pair of electron moves into the benzene nucleus, is moving into the benzene nucleus. So I repeat, the lone pair of electrons present on a nitrogen is released towards the benzene nucleus, thus creating thus creating a negative charges in the ortho and para positions. I repeat, when the lone pair of electrons from nitrogen are released into the benzene nucleus, the movement of electrons are found to be more in case of para and ortho positions. So, in such cases, if the second incoming group approaches aminobenzene or aniline, the NH2 group directs the incoming groups into ortho and para positions. This results in the electrophilic substitution reaction. Since ortho and para positions are negative, this type of compounds are susceptible for only electrophilic substitution reactions. So I mean to say, this compound, now aminobenzene, has more electrons or negative charge in ortho and para positions, and this electron rich ortho and para positions can be attacked only by electrophiles. So, electrophiles are nothing but electron deficient species or electron poor species. Thus, electron poor species will definitely attack the electron rich species, and thus the products formed can only be ortho or a para product. Next is the negative mesomeric or the negative resonance effect. So it's quite opposite to the positive resonance effect or positive mesomeric effect. So here in this case we find or we see the migration of pi electrons or lone pair of electron towards the atom or group that is attached to the conjugated system. So I mean to say, electrons, pi electrons from the benzene ring will move towards the atom that is attached to the benzene nucleus. So in the example of nitrobenzene, we see the pi electrons moving towards nitrogen, thus creating positive charge or electron deficiency only in meta positions. Electron deficiency in meta positions. Now, in this case, if a nucleophile approaches, it will be definitely attacking the meta positions because the ortho and para positions are positive in charge. So, this compound can now be susceptible to nucleophilic substitution reaction. So, only a nucleophile can attach such a compound. Sorry, a nucleophile can attack the compound because meta position is electron deficient and a nucleophile is electron rich.